Hello everyone, welcome back. Let's continue with the design principles. So, today we will talk about how to avoid bending stresses and why we need to prefer tension and compression. So, we are talking about design for stiffnesses and therefore, it is very important that we make a structures or make design where the members are preferably in tension and compression. So, is basically relates to the triangulation again, and if we refer to the bridge design or the structured design for machine frames or for any civil applications and looking for high stiffness and rigidity, that is where we are talking about triangulation and talking about tetrahedron structure in 3-dimensional space. And in all those designs, what we realize that the members, the individual components are typically either in tension or compression. So, if we follow that, then what we realize that most of the members are in tension and compression, and we try to avoid any kind of bending loads if you are looking for high rigidity and high stiffness. So, one of the reason why we are looking at tension and compression and why we want to avoid bending loads, I think we can see from the example. If we apply any kind of force here on this structure, so it is a beam, cantilever beam. So, what will happen if we look at the stress distribution in a beam? So, this is kind of the distribution usually we see. So, under this kind of conditions, so it is a linear, and the topmost layer will be in tension and the bottom layer will be in compression. And if we see these sections, middle section, they are not taking much load, or in a way we can say they do not contribute much. So, in terms of material usage, it is not very optimized. So, that is why we say that the material at the midpoint of the section is unstressed and contributes nothing to the strength or rigidity. So, this is the bending distribution, the stress distribution because of the bending. Similar thing we see in case of torsional loads also, and when we apply any kind of torsional load, the torsional stress, so it varies from maximum on the outer fibers to 0 in the center of the section. So, in terms of material utilization, what we find that the bending or torsion is not very good. On the other hand, if the member is in tension or compression, so if this is the case and there is a longitudinal force applied, so this is the distribution, the stress distribution here. So, and it will be tensile in nature in this case. If it is a compressive, yes, it will be a compressive load. So, in both cases, if it is tension or in compression, there will be constant stress throughout the section. And therefore, in terms of material usage, what we realize that every section is participating and taking the load. So, it is shared by each and every section of the component. So, one of the design principle is, if we are looking for high stiffness and rigidity, is to get uniform stress and try to design for that. So, what we realize in bending and torsion, much of the material contributes nothing to the carrying load, or what we can say is the only the outermost layer or top or bottom layer is significant, and therefore, we try to focus on that. What we also find that even though the material is the inside material is not stressed, but since the outer layer is highly stressed, they can go under failure, because the stresses are highest on the outer layer. So, for that reason, bending and torsional loads are inefficiently borne by structural elements, whereas if we look for tensile members, they are uniformly loaded and they take the load quite efficiently. So, here is a illustration, and I think in most of the civil application what we talk about is the I beams, and we can, if we try to just relate the design principle, then we will be able to understand why I beams are used more often. So, if you see here, because of the bending load, of course, the top and the bottom layer, they are taking the maximum load. So, either in tension or compression. So, the material is more on the upper and bottom layer, and the middle section is only providing the triangulating structure. So, here is a triangulating shear wave. So, therefore, I think in many of the designs, structural design, we see I beams which are used more often if it is loaded under bending. Similarly, if it is for torsion, this is the shear stress distribution, this is what we see here. It is a maximum here on the outer edge and 0 at the center. So, what we realize that is the only the outer section which is more important, and we can remove the inner section and we can get rid of the material, and that way we can make full use of the material what we have. So, most of the time we prefer to use hollow tubes if there is a torsional load. So, wherever we need some flexibility, compliance, there we go for bending or torsion. So, for instance, if we take this design, this snap fit, we want that under loading this should deflect and get it locked here. So, it comes in the wedge, and then so when we insert, try to insert, it should flex, we can insert it easily, and then it springs back and provide us the locking. So, bending is an advantage for parts which requires flexing, right. So, for instance, is a snap fit we are designing. Similarly, we can also say for torsion. So, next design rule or principle, what we can say is improve designs with self help, and earlier I mentioned this is what generally I refer to is mechanical intelligence. So, we can do a lot of things at the design stage, at the conceptual stage, which will help. So, the requirement is such that the requirement itself reinforce the performance. How? So, what we look here is, so when we say self help, what we are trying to say, use the applied load to improve the performance. So, the applied load itself, it enhances the performance. So, how? By creating new and useful forces or transform or redirect. It can also do balance either or existing loads or help to distribute the load. So, we try to find a mechanism so that this can be achieved. So, for instance, if you are looking at self-help that creates forces, we have very good example here, and I think we have almost at every home, we have pressure cookers for cooking, but what we realize here that the pressure form seals, so here O-rings or any internally mounted doors, they use self-help to create robust areas. So, if the pressure is built, the design is such that these O-rings or the seals we use, they further provide more sealing, and that way it can provide robust sealing. So, this can be used to design any kind of pressure vessels, fermentation tanks, autoclave systems, or any kind of pressurized system we can design using these principles. It is just for the game, but this concept we can also use. So, it is a trap, and what you see here, this is a very simple toy and is made out of these kind of things. What we realize that when we insert our finger, try to bring it from both sides, actually the diameter increases. So, you can insert your fingers very easily, but now when you try to take out your fingers, so try to pull, actually it contracts, and because of the friction the two ends will stick, and as you start pulling, the diameter will decrease and it will further grip the fingers. So, it is very difficult to take them out. So, you can insert very easily, but taking out by force is very difficult, because harder you pull, the tighter it grips. So, this is kind of self-help we are talking about, and these kind of things can be implemented in a lot of designs. Other is, can you redirect the forces? So, for instance, in the design of seizures, left hand, right hand, you have a different kind of different seizures for right hand and left hand use, and the way it is designed, as you move, they also bring the blades together to get a nice cutting effect. So, the seizure shearing action is getting improved by the hand movement. Many times we can also use self-help to balance forces, and the idea is to either balance or neutralize or minimize the undesirable effects. How? So, one of these ways is to use counterweights, and they are used in many of the bridges design or the elevator designs. So, what it says, it increases the weight, yes, but it also eliminates moment in the structure, and therefore, it can help in the design, and so it also brings some kind of symmetricity in the design and help. Other is like it's normal doors, if there is a strong wind, very difficult to open. So, this is one design where it's pivoted at the center, right. This is the axis we are talking about, hinge axis. So, if it's offset, it's very difficult to open if it's there is a strong wind. So, the idea is to get it at the center. So, and you make it articulated, and if you want to open, even if there is a strong wind, because it will counteract, and it's easy to open and move it aside. So, this is also a very good example of self-help. Another commonly used and many times we may not realize, but if we have like ball joint kind of thing, and yes, if there is a small load, the area of contact actually it deforms and uh, the area of contact will be small and it will get distributed. Moment we have larger loads, this area increases and that is how it supports the bigger load and helps in counteracting the load. There are several such examples. One can think of also how the railways are steered and how the wheel design is done so that it can easily steer on the track. So, actually it is a very good example and one can check, one can see and try to understand. There is no steering wheel, it steers on itself and as depicted here, if there is a right turn and the way the wheels are there, it slides. So, there will be centrifugal force here and because of that it slides. So, what you find that on the left it is larger diameter, on the right you have the smaller diameter and that change in the radius or the diameter, it will make it to steer to right. Similarly, if it is a left, it will slide to the right and then you have a smaller and a larger radius on the outer side and it can turn to the left. So, very good example of self-help here. I think very good designs like governors. So, yes, if the speed is very high because of the centrifugal action, it will be thrown out and it will collapse, right, and then it will try to balance. So, also control the fuel intake and all those things. So, the governors in the old machines, diesel engines you can see is a very nice design. At the same time you can also think of centrifugal clutches, overrunning clutches, and as it spins all these things will just spread because of the centrifugal force and they will come in contact with the outer drum and provide the braking action, so that this speed can be reduced, and as the speed reduces it is loaded with the spring, so it comes back. So, it can so very good designs and these we can use in our products or in machines to control the speed. So, again it is a very good example of self-help. So, there are many such examples as we go across and we will discuss some of these designs in detail and there are a lot of compliant versions. And the next design principle or rule is to manage friction in mechanisms. And whenever we talk about precision machines or talking about high repeatability, invariably we will be talking about friction and how to manage friction in mechanisms. So, this is very important topic when we are talking about precision machines. And the reason is nature, the way the two surfaces come in contact and the friction is defined, that creates a lot of problem and there are a lot of uncertainties and that gives rise to a lot of issues, and therefore, we try to avoid any kind of sliding friction, sliding contact. If there is any, we try to maximize the length between the linearly guided components. So, for instance, if we have drawer and those kind of things, we might have seen that. If we have to choose between rotary or linear, we always go for rotary motion. If we have to use any kind of bearing, always go for rolling element bearings rather than the sliding one, and if possible try to use flexures to eliminate friction. So, why we are talking about friction? Why you want to avoid sliding friction in the first place? Because managing is very difficult. And what does it mean? Near zero speed is a stick slip behavior. The two components try to stick, and as we try to move, they suddenly move. So, this stick slip behavior is predominantly there because of different values for the coefficient of friction. So, when it is a static and when it is a moving. So, the difference between the static and the dynamic coefficient of friction, that gives rise to these kind of behaviors, and moment we encounter stick slip behavior, it is very difficult to achieve any kind of precision. Another thing is the frictional coefficients. So, it is not a fixed value, right. Many times in the books, in the handbooks, we refer to some numbers, but there is no one value to use. In our calculation, we can always use a number, but there is a wide variation, and it can vary on any given day depending on the temperature, on the loading conditions. There are various parameters. So, it is very difficult to control. It varies depending on the lubrication status of the surfaces, surface finish, and it leads to a lot of surface damage is like galling or wear. So, since it is a statistical parameter, the surface, talking about the entire surface, talking about the lubrication status over the surface. So, but the contact might be at certain locations only, and if we are you do not know, then we have to deal with this wide variation. It means it is highly unpredictable. So, therefore, it is very important to avoid if it is possible. So, again, so we are talking about maximizing the length of linearly guided components, and why we will also talk about those things later in the course, but it is a rule of thumb generally. So, we try to maximize the length and basically to avoid this kind of behavior. So, a sticky drawer. So, if it is small, then very likely it will get stuck. So, we have to then push and pull very gently. We try to adjust and then do that. What it also says, linearly guided components jam when insertion force is inadequate to overcome the friction of the guided contacts. So, if it is getting jammed, the edges will get stuck, and no matter how high is the force, the friction force will also increase, and these kind of drawers will get jammed or the components will get jammed. And that is why whenever we try to assemble, suppose bearings, it is very important to use tools, proper tools. Otherwise, it is very difficult to take out the bearings or even assemble the bearings, or they can easily damage the surfaces. So, this is one example. So, if you look at it, yes, it is highly exaggerated, but yeah, it comes in contact at these places and there will be friction, and there is any Like if the load is not symmetric, if it's off, it will create undue forces and then it will get jammed. So, some illustrations. So, if we take these kind of examples, what we realize that very good examples here. So, many of the designs in automation system or in robotics we frequently use. So, we have a carriage and then we have a linear bearings here and we provide the two guides. What is the challenge here? What are the issues? So, what is saying the center line? So, what we realize here, the two center lines for the guides, how to get it aligned properly, how to get them parallel, because it's supported here, here there are 4 holes. How exactly they can be located, right? The distances between the two, yeah. Also the distance between the two linear bearings on the carriage. There are so many over constraint here, and only way to address is, yes, we can define very high tolerances. So, the cost will increase. At the same time, if we do not want to do that, then we had to compromise on the design. So, we provide a lot of clearances. So, a lot of backlash and movement there. So, it is a very poorly designed, and one of the reason is the over constraint here, how to put the two guides together and make them parallel. So, if we design this way, we will face a lot of problem and there is always a limit. Of course, if we want to address the issue, we may find a way to address this over constraint and we release certain degrees of freedom, and then if it is exactly constrained, then we may find that it is a very easy and it is very easy to achieve certain repeatability. So, it might be off, but it is a repeatable, and that can be that we can always offset using proper controller or even adjustment we can use to address that kind of issues. So, next is why rotary motion over linear motion. So, linear motion we understand that a lot of jamming issues, the over constraint we have. If it is a rotary motion, a lot of those problems can be eliminated, but we also realize that the loading itself provides some moment and it always try to bring it down. So, of course, in this case also there will be some uncertainty, but it is always within certain limits and that we can address. So, some more examples. So, here example of linear sliding action, and here is the pivoting lever action, and we know that even a simple soap dispenser, if you are designing which one to use, which one is better, and we may have encountered this kind of issues when we are using this kind of dispenser at home or even the shopping malls or in the public places. So, they always have a problem when because tries to there is a gap and try to stick and slip. So, many times it gets jammed also, but if it is a rotary, you apply the force. So, there will be always moment and it tries to rotate, and it is very easy to use. So, wherever possible, try to eliminate any kind of sliding action with the rotating action. And here there are many kind of rolling element bearings, ball bearings, roller bearings, needle bearings, taper bearings, recirculating ball bearings also. So, If we talk about ball screws or even the linear guides these days, they have recirculating ball bearings, ball linear bearings, and although it looks sliding, but inside there are rolling elements, and we still get the rolling element bearings there, and then we can avoid the problems related to jamming, which is generally we encounter when it's sliding only, if there is a sliding pair. One of the reason why you also want to use rolling element bearings is it's a simple, right? So it's a simple to use, but if we open any bearing, it's a highly complex, but then it's a hidden, it's a intrinsic, and we don't have to worry. So our designer usually they don't have to worry about how the bearings are made or designed. You look for the standards, you look for the loading, the life you want to have, and you follow the design methodology, the what is the selection method, and we just do that. So how the bearings are made, normally the designers they are not normally concerned. So yes, it's a simple to use, and the complexity is intrinsic. One of the way to also address friction related problem is to just eliminate it. Yes, many times it's not possible, but wherever possible can we do that. So what we realize that in today's time and many of the machines or product, what we realize that the range of motions are very limited. And if that is the case, we can always remove those conventional joints using rolling element bearings, and we can replace them with the flexure elements. So this is one topic we will be covering in detail in this course, different kind of flexures, component mechanism, and the idea is to basically eliminate friction related issues so that we can get rid of the white noise, the randomness in the design, and that way we can achieve high repeatability. Even though if we realize that the range of motion is very large, we can always go for coarse movement and the finer movement. So coarse action, for the coarse action we can use conventional design, conventional bearings, but as we approach, we move to this kind of flexure mechanisms or compliant mechanisms and try to achieve better repeatability. And what we also realize that these flexures are basically members in bending or in torsion. So here we are looking for low stiffness, very large compliance, and therefore we just do the opposite. For stiffness we go for tensile or compressive load. So we go for designs where most of the members are in compression or in tension, but wherever we are looking for compliance, we go for torsional and bending loads. So this is one example where we can guide any member axially, but it can move back and forth, and it can easily move few millimeters without any problem. So since it's an elastic mechanism, it always comes back to the same location. Even if it's a nonlinear, it's a highly repeatable. So the predictability can be ensured, the precision can be ensured, and we can think of achieving a precision level of the micron or even the nano level. So as I mentioned, consider using flexures for precise frictionless motion over limited deflections. So is for a smaller range of motions. We eliminated friction, so lack of friction means predictable and reliable. So, both is ensured, both are ensured when you are using flexion members, which is not applicable if there is a friction. So, it is very important that we focus on these kind of elements, and once you go back and if you look at the machines which are designed for very high precision or very accurate systems, whether it is pointing devices or some instrument measuring at that scale or microscope, different kind of microscopes used for material characterizations, for any kind of machines is for semiconductor industry. You will find many of these mechanisms embedded in those machines, and I think after this course I am sure that we will be confident and one will be able to know or explain why those things are there and what is the importance, and most likely we can also develop and build those machines and try to achieve those precision levels, or ultimately using proper control, proper vibration isolation techniques, we can achieve the accuracy in the order of nanometer, or what I can say in the atomic orders. So, today we try to close it, and what we learned, the elementary rules, or what we can say design principles in general. What I also try to emphasize that these things are not something new, it is well known to people in the industry. If you are involved in designing products, most of the experienced designers, the machine builders, they are aware of these issues. They apply these rules knowingly or unknowingly, because it is developed and they understand that it works. So, as a fresh engineer or as a student, I think one should know and start practicing these things, and what we realize that if we just follow these simple rules, it is very easy to design systems at low cost with a very high performance, very good performance, repeatable performance. There are still few things we will be talking about which may be required if we are going to design systems for very high precision, for ultra precision movements. So, going to the scale of submicron level or atomic level, and we will talk about those principles. But what I would say, these are must we should apply, we should know when we are involved in any kind of machine design, product design, or even talking about automation system, robotic systems, for whatever application. So, there is no shortcuts. If we just take these things in perspective, and if we remember these things, we will always able to achieve things with high precision, and with high precision we will get a very good performance, very good reliability and quality. Things will not fail, and we will get confidence to develop systems on our own. Yes, there are many things here that we will learn only while doing it. So, yeah, unless we take that step and take that leap of faith, we may not be able to achieve things and yeah, then we will be only dependent on others. We will be only buying, importing machines and products from abroad, from other countries. But if you want to be self-reliant, want to successfully achieve Make in India, Made in India concept, keep these things in mind and let's move, let's start designing things for the future, for the high-end application, for our own good. And these are very good references. These are the books, and many of the content are from these sources. There are the pictures, the materials, many of them are from the internet. It's only for illustration and for better explanation. But these goods are excellent. If you are designer and interested to build machines, one should definitely refer to these books. So, book by Blanding, Exact Constraint Machine Design Using Kinematic Principles is a very good book talking about constraints and how to achieve degrees of freedom, by Professor Skakun, Elements of Mechanical Design, again a very good book, and a book by Professor Summers, Design Principles for Precision Mechanisms. So, these are the three references for the time being I am mentioning, and these are very good books, not very thick, very easy to read, and one can easily refer to these books and can design stuff for that. And we will cover most of the content from these books, and we will discuss during the course. And as we move on, if you face any problem and if you have any questions, please write to me or send comments. We will take up those questions and try to address some of them and try to learn more. Okay, thank you.